You will find the last question, especially the last question is from atomic physics. Okay, in this question, bismuth 214 is a radioactive. When they say radioactive, it means it is emitting out radiation such as alpha, beta, and gamma, which is having a half-life of 20 minutes. So after every 20 minutes, it will change half of its original value. The nuclide notation of a bismuth 214 is 21483 with Bi. State the composition of the nucleus. Composition of the because the nucleus consists of neutron and proton. So how many neutrons are there? And how many protons are there? So there will be 83 proton. But how many neutrons are there? That is 214 minus 83. So that's equal to 131. So 131 neutrons are there. That's a composition of a nucleus. Because they ask composition of nucleus, if you write electron, then your answer will not be correct. Why? Because it's a nucleus, so it does not have electron in the nucleus. Electron only produced from the nucleus when there is a beta decay. But originally it is not present. Then bismuth 214 decay by uh, beta decay to an isotope of polonium. Complete the equation for the decay. When there is a beta decay, the atomic mass remains same and atomic number increases by 1. And what is the sign for beta? It is 0 and minus 1. So what will be at the top for polonium? This beta or electron is the same thing. You can write, it's already symbol is given, so we just have to write the number. 0 here means it does not contain neutron or proton. And the charge electron is there, that's why minus 1. So at the top, it will be 214. The mass, when there is a beta decay, the atomic mass does not change. What about atomic number? What should be the number for polonium? Because the total on the left hand side should be equal to total on the right hand side. If I write 83, then it will be wrong. Why it will be wrong? Because 83 minus 1, that make 82, but we need 83 here. So this should be 84. So when there is a beta decay, atomic mass does not change and atomic number increases by 1. Is it clear? Why the atomic number increase? Because a neutron breaks into proton and electron. So proton number increases, that's why atomic number should increase. That is from the journal equation which we discussed last week. The count rate from a sample of a bismuth is 360. Predict the count rate from the sample after 60 minutes. They already mentioned the half-life is 20 minutes. So it is giving 360 radiations with a half-life of 20 minutes. That's because it's a continuation of the question. So we want the number of radiation after 60 minutes. So after 20 minutes, what will be how many radiations will be there? That's 180. Then after further 20 minutes, what will be the radiation? 90. Then after further 20 minutes, what will be the radiation? 45. So this will make total duration 60 minutes. So after 60 minutes, we have 45 counts or radiations per second. Is it clear? Then for the next part, state two of social, economic, or environmental issues involved in the storage of the radioactive material with a very long half-life. Like if a radioactive material is having a very long half-life, so it will remain radioactive for a longer period of a time. So any two social effects or economical effect or environmental effect or issues, not effects, basically issues involved in the storage. Directly I will show you, because there are many things are there, but these are like if you are mentioning a economical effect, so it will increase because this thing will remain radioactive. Yeah, that's right, people scared of the effect mute. So high cost is there for shielding or storing, and reduction in tourism, like reduction in tourism, for example, if there is a place where they are dumping a radioactive or using a radioactive material, and that radioactive material is having a greater half life, so it will take a lot of time to be stable, so you don't find tourists at that place. The social effect, the fear of cancer is there, and it can cause people to move away from the environmental effect, mutation, crop mutations, and it may enter a leakage, enter a pollution of atmosphere or water supply. Here, pollution of atmosphere, it will make the because radiation can ionize the air. In that sense, it is mentioned pollution of atmosphere. Is it clear, this part? Because it was having many possible answers, that's why I was showing you the marking scheme. Then another paper, May June 2017, paper 4, variant 1. Okay, in this question number 11, normally you'll find the last question is from atomic physics. A radioactive source is tested over a number of hours with the radiation detector. The readings are shown. The time is there in the detector reading. Use the reading to suggest the value of the background counts during the test and to determine the half-life. First, from this reading, how I can determine the background? Look, first, what is happening? This is because of source and background, both. But the readings are continuously decreasing till this point. And after this point, the reading are more or less same, like 17, 21, 20, 19, 20, 18. So what it shows that here I'm not recording the source radiation, I'm only getting the background radiation. It means the source is completely stable now and the radiations are coming from the background. So you can take an average that is acceptable, or you can just take any value because this will have a range of answer. It will not have fixed answer. So example, I took 20 as a background radiation. Is it clear why I took background radiation from this region? Because originally I'm getting a radiation from source and background, surrounding or background having the same meaning. But as the source is getting stable, so amount of radiation which are coming out from the source are decreasing, and eventually, or if the source is completely stable, it is not, because as it is emitting out radiation, it is gaining stability. So as the source is completely stable, then what happened? The only radiation with the detector will record, that is due to the background. So you can take an average or you can use any value from this as a background rate. Now what we need a half-life. So as we know, the detector reading is equals to source plus surrounding or background. So the first value on the detector is 324. 20 are due to background. How many radiations are there from the source? So 304 radiations are from the source. Then after half-life, if there's a half-life, after half-life, only the source radiation will be half of its original value. So half of 304 is 152. So this will be 152. This will be 20. So the detector reading will be 172. But the problem here, I don't have any value of 172 in the reading. So I cannot use the time interval to find a half-life. Then after another half-life, what will be the source radiation? What is half of that? Is 76. And the background are 20. So detector will record 96 radiations. So basically what happened? 324 changed to 96. Originally, the detector reading were 324. Now the detector reading are 96. So changing from 324 to 96, how many half-lives are there? Because when the detector reading changes from 324, it is taking 324 to 96. It is taking 1 hour. It means the two half-lives, because these are two half-lives. So two half-lives are taking how much time? Changing from 324 to 96. So two half-lives are taking 1 hour. So one half-life is equals to 1 divided by 2, which is equals to half an hour or 30 minutes. Is it clear? So first we work out how much time it will take, or how many half-lives are there in the time interval when it changes from 324 to 96. So changing from 324 to 96, there are two half-lives. The half-life is constant for a material. If you have, example, if you have 100 gram of a sample, if 100 gram is taking 5 minutes, then 50 gram will also take 5 minutes to convert its original value. Then 25 gram will take into 12.5, also 5 minutes. No, half-life is constant. For every material, from element to element, the half-life can change. For one element, the half-life, or one substance, the half-life is constant. Here, both answers are acceptable. You can write 0.5 hour, or you can mention 30 minutes. Another equation which you have to complete for a beta decay: hydrogen 3 tritium has 1 proton and 2 neutrons. The nucleon number is 3 and it decay by emitting beta particle. Complete the nuclide notation to show this. So this is hydrogen. What number should I write at the top? What is the mass number of this isotope? 3. And what is the atomic number of this isotope? 1. It emit out beta, so symbol for beta 0 minus 1. What will be the number above X? The suffix, superscript. The superscript,
Same.
it will remain same because atomic mass does not change. And what about the subscript? The subscript. So it will be 2. Because 2 minus 1, that will make 1. So this is how we complete equation, and it's of 3 marks. Is it clear? So total about 7 marks, and this is the last part of atomic physics question. This is a Rutherford experiment. The arrow in the figure 11.1 shows the path of alpha particle moving toward the gold nuclei in a thin foil. On the figure 11.1, complete the path. Alpha particle 1 is actually hitting the nucleus. So what I will do? Passes through, deviate, or reflect? It is directly hitting the nucleus. This is not an atom, this is a nucleus. So when it hit the nucleus, it will bounce back. And look, practically this does not happen. It hit and bounce back. Practically before striking, due to electrostatic repulsion also, it bounced back. Alpha particle 2, it will pass straight, deviate, or bounce back? It is coming closer to the nucleus, closer, not direct.
Deviate.
So it will deviate. Because it is closer, so it will experience repulsion, so deviate. And alpha particle 3, it's far away from the nucleus, so it will pass straight. Is it clear?
Yes, sir.
No, it does not need to touch the surface to deviate. It's not like you can make you can draw in this manner, that is correct, or you can continue from there, that is correct as well. Even if you make hit and bounce back, this is acceptable. But what I'm saying, practically this does not happen because of electrostatic repulsion as well. It bounce back. But you can draw, these both are acceptable. In O levels, there are certain things which are not 100% correct, but they are acceptable according to the level. Okay, in this question, a radon 222 is radioactive and it can be represented as Rn 222 and 86. For a neutral atom of a radon state, the number of the protons, how many protons are there?
86.
How many neutrons are there? 222 minus 86, what's the answer? 136. How many electrons are there for a neutral atom?
86.
86. Then the next part, a radon 222 nucleus decay by alpha particle emission. When it decay by alpha particle emission, the atomic mass decreases by 4 and atomic number decreases by 2. And it convert into polonium. So it convert into polonium and alpha particle is there. Or you can make alpha particle first and polonium at the last. So it, because for alpha particle, it is fixed 4 and 2. What should be the superscript for polonium?
218.
218. And what is the subscript?
84.
84. Radon 222 has a half-life of 3.8 days. Means after every 3.8 days, it will become half of its original value. At certain time, a sample contains 6.4 exponent 6 radon nuclei. Calculate the number of the alpha particle emitted by radon nuclei in the following 7.6 days. So basically, what we have to do, we have to find how many radon nuclei decay, because calculate the number of the alpha particle emitted by radon nuclei in the following 7.6 days. So how we work out? So 6.4 into 10 to the power 6 radon nuclei are there. So after a half-life, it will be half of its original value. In exponent, better tell in exponent. Like example, look, when it
Sir,
is
but
emit,
it's
yes,
7.6 days.
what?
But it's 7.6 days. 7.6 days.
Yes, 7.6 days, but we need after the half-life is 3.8 days, so it means after every 3.8 days, it will be half of its original value.
Yeah, so after 7.6, it will be like 0. It will be nothing.
Not zero. It is always done step by step. After half-life means after 3.8 days, it is not done directly. You don't solve directly, and it is not necessary that after 7.6 days all will be stable. Maybe some samples still unstable, so you cannot say directly. Now 6.4 exponent 6 was the original. After half-life, half will be stable and half will be unstable. So after half-life, half of 6.4 is 3.2. So 3.2 into 10 to the power 6 will be stable. Stable means does not emit out radiation. And 3.2 into 10 to the power 6 are still unstable. Unstable means emitting out radiation. Then after further 3.8 days, because 7.6 days means total 2 half-lives will be there. If one half-life is 3. So after further 3.8 days, or the total interval of 7.6 days, it will be 1.6 into 10 to the power 6 will be stable, and 1.6 into 10 to the power 6 will be unstable. Unstable means does not emit means still they can emit out radiation. Now the question is, how many, calculate the number of alpha particles. So when they're emitting out alpha particle, they become stable. So how many are stable? That will be the number of alpha particle. So how many of them are, because when they're emitting out, as you solve the first equation, you can see the previous equation. When radon emit out alpha particle, it become polonium. So how many radon atoms become polonium? That will decide how many alpha particles will be emitted. When one atom of radon becomes stable, it will emit one alpha particle. So how many stable atoms are there? How many atoms are stable after 7.6, total 7.6 days? So 3.2 exponent 6 and 1.6 exponent 6, these are the stable atom. So total number of stable atoms will be 4.8 into 10 to the power 6. So if these are the stable atoms, how these stable atoms are formed? Because radon emit alpha particles. So how many alpha particles will be emitted? That will be same as 4.8 into 10 to the power 6. Is it clear? Because the number of the alpha particle emitted out depends on how many atoms become stable. So first 3.2 exponent 6 becomes stable, so means this is the number of alpha particle emitted out. Then 1.6 exponent 6 becomes stable. So this is the number of the alpha particle becomes emitted out. So the total, it will be 4.8 exponent 6. So it is not necessary that after 2 half-lives or 3 half-lives, all the sample will be stable. It may be or it may not be. You have to go through the steps and work out how much sample will be left after certain half-life. Okay, in this question, a nuclear equation below shows a decay of plutonium to americium by beta particle. State the quantity that is represented by Z. What is number Z here? Letter Z. What is the number? Quantity that is represented by Z. Like which quantity we represent? The number is at this point. What we call Z. Z. The name, it is called atomic number or proton number. So atomic number or proton number.
Z is proton number.
Yeah. Then what is the numerical value of a Z? What is the value of Z here? So Z is equals to 94. Basically, you can check with, because 95 minus 1. So that on the right hand side, we have 94. So on the left hand side, we should also have 94. And the top 214 plus 241 plus 0. So 241 is
Sir,
there.
how 94? Sir, how 94?
Because it's a beta particle. So beta particle is 0 and minus 1. What is the total number in subscript? 95 minus 1. What is 95 minus 1?
But beta takes away electrons.
Yeah, beta is electron. So when beta is electron, the proton number increases. That is why this Z in place of Z should be 94.
Yes, got it.
So if this is 94, the atomic number increases by 1 because proton number increased by 1. So Z should be 94. Then americium nucleus decay by emission of alpha particle into neptunium Np nucleus. Now complete the equation. Americium is there and it is emitting out alpha particle. What will be the superscript for neptunium? 237. And what is the subscript? That will be 93. In the next question, the half-life of americium nuclide is 470 years. Means after 470 years, it will be half of its original value. A sample of the nuclide contain 8 exponent 14 atoms of americium. After some time, 6 exponent 14 atoms of americium have decayed. Calculate the time required for this decay. Means we have to find that total when 6 exponent 14 atoms of americium decayed or become stable, then how much time it will take. We cannot use a ratio here. Ratio is only used when for one value you are taking, like for one stage, but because it's a 2-stage, you cannot take a ratio. If you try to solve half-life question with a ratio, you will not get a right answer. Look, in the beginning, we have 8 exponent 14 americium atoms. So in the beginning or the start, we have 8 into 10 power 14 americium atoms. Okay. The americium atom, as we know, when it emit out radiation, it changes into neptunium. So after half-life, after first half-life, how many neptunium will be there and how many americium will be there? Atoms. 8 exponent 14. What is half of 8 exponent 14? That will be 4 exponent 14. So after half-life, 4 exponent 14 will be neptunium and 4 exponent 14 will be americium. Then after further half-life, so how many have decayed? Because we want to find a time interval when this much atom of americium have decayed. So right now, how many atom decayed? 8 exponent 14 have decayed now. But we want when 6 exponent 14 will decay. So after another half-life, americium will change into neptunium, half of it. So this will be 2 exponent 14. And this also 2 exponent 14. So if you are left with 2 exponent 14 americium atoms, how many have decayed now? First 2 exponent 14. Both are not stable. One is stable. One is relatively stable, like this is converting into stable. In terms of radioactive, both are radioactive, but what we are considering americium is unstable and neptunium is stable. But in terms of radioactivity, actually both are radioactive, both are unstable. Neptunium will decay according to its half-life, but we are finding for americium only. So in the beginning, you was having 8 exponent 14 americium atoms. And after 2 half-lives, you are left with 2 exponent 14 americium atoms. So how many americium atoms have decayed or break down? So total 6 exponent 14 atoms have decayed. So and how many half-lives they are taking? They are taking 2 half-lives. So if one half-life is 470 years, then the total time it will take when it decay into 6 exponent 14 atoms of americium have decayed, it will take 940 years. Is it clear? Is it clear, this question? Look, in the question, they're saying after some time, 6 exponent 14 atoms have decayed. We need a time. How much time it will take for 6 exponent 14 americium atoms to decay? So in the beginning, we were having 848 exponent 14 americium atoms. After half-life, 4 exponent 14 will be stable and 4 exponent 14 will be unstable. Then after, so how much time it will take? That will take 470 years. Then an unstable one will further decay. It will be 2 exponent 14 will be stable and 2 exponent 14 will be unstable. Now, how many have decayed? This is a part which is decayed. So 4 exponent 14 plus 2 exponent 14, this is a part which have decayed. So when 6 exponent 14 have decayed, how many half-lives are there? There are 2 half-lives. 470 plus 470, that is why it is 940 years. Is it clear? So these are the questions related to atomic physics. So we are done with atomic physics as well. We'll do more questions. Yes, what's the question? So we completed this atomic physics as well. Tomorrow we'll discuss the weekly homework as well as some more questions from atomic physics. Submit the weekly homework before the session along with your doubts.